When the James Webb Space Telescope turned its powerful instruments toward Proxima Centauri, a red dwarf star located 4.24 light-years from Earth, astronomers were hopeful that the resulting data might bring humanity closer to answering one of its most profound and enduring questions: are we alone in the universe? Of particular interest was Proxima Centauri b, an exoplanet orbiting within the habitable zone of its star. This planet had long captured scientific interest due to its Earth-like mass and favorable position for supporting life. While researchers had hoped for intriguing results, even the most optimistic among them did not anticipate the magnitude of what the Webb telescope would reveal. Through detailed spectroscopic analysis, the telescope detected not just basic atmospheric components, but complex chemical markers that strongly hinted at the presence of biological activity. These signs suggested that life might already exist on this nearby exoplanet. The breakthrough came from a series of infrared spectroscopic observations conducted using two of Webb's most advanced tools, the near-infrared spectrograph NIRSpec and the mid-infrared instrument MIRI. These instruments allowed scientists to examine the atmospheric makeup of Proxima b with an unprecedented level of detail. What truly surprised researchers wasn't merely the detection of gases like carbon dioxide or water vapor gases, which can be produced by geological or chemical processes, but the presence of methane, oxygen, and ozone coexisting in sustained and balanced concentrations. On Earth, such a trio is typically maintained through biological processes. Methane, in particular, is unstable in an oxygen-rich environment and would normally degrade quickly unless actively replenished. The stable coexistence of these gases pointed toward continuous biological activity. Adding to this, scientists observed seasonal fluctuations in the concentrations of these gases, reminiscent of Earth's carbon cycle. These periodic changes hinted at a functioning biosphere that inhaled and exhaled in sync with the planet's seasons. Such fluctuations were not one-time anomalies, but consistent, regular patterns observed over multiple orbital periods, further reinforcing the theory that biological processes were at play. Webb's high-resolution photometric instrument also detected unusual reflectance patterns across Proxima b's surface. Variations in albedo, the amount of light reflected from the surface, were seen across different regions and times, suggesting dynamic surface changes. Some researchers interpreted these patterns as being similar to vegetative or microbial blooms that fluctuate with sunlight, akin to how phytoplankton blooms in Earth's oceans or vegetation grows and decays across terrestrial biomes. This theory gained even more traction when Webb observed red edge signatures in the planet's light curves. On Earth, red edge reflectance is a characteristic of photosynthetic organisms, particularly those containing chlorophyll. Scientists proposed that similar features on Proxima b might be caused by alien photosynthetic life forms adapted to the redshifted light of a red dwarf star. This suggested the presence of biological pigments tailored to Proxima Centauri's light spectrum. Another significant discovery emerged from temperature and pressure readings derived through transit spectroscopy and modeled using radiative convective equilibrium. These models indicated that Proxima b could sustain surface temperatures ranging from 5 degrees Celsius to 30 degrees Celsius within its equatorial zone. The planet also appeared to have cloud cover and an active water cycle, including signs of precipitation, potential bodies of liquid water, and even storms. These findings offered physical evidence of a climate that could potentially support life not just in theory, but in measurable, observable terms. Although no single indicator would be sufficient to confirm life, the combined presence of biosignature, gases, seasonal variability, red edge reflectance, and an active hydrological cycle made a compelling case. Statistically, the odds of all these features appearing together on a lifeless planet were extremely low. With mounting evidence, the scientific community began to shift from cautious optimism to growing confidence. The James Webb Space Telescope had uncovered evidence of an alien biosphere on Proxima b. The implications of this discovery extended far beyond astronomy. From a biological standpoint, it challenged the long-held notion that life as we know it is unique to Earth. If life could arise independently on Proxima, be a rocky world orbiting a volatile red dwarf, then the basic requirements for biology might be more common across the universe than previously assumed. Life, rather than being a cosmic rarity, could be a universal phenomenon emerging wherever environmental conditions and chemical ingredients align. This revelation revolutionized the field of astrobiology. Once considered speculative and fringe, the field had now received powerful validation. Scientists who had spent decades theorizing about the environmental and chemical requirements for alien ecosystems now had a real-world laboratory in Proxima. These findings allowed researchers to build new models of evolution that did not rely on Earth-like conditions. They began to ask questions such as, how does life evolve under the harsh flares of a red sun? What biological adaptations allow survival in environments rich in ultraviolet and X-ray radiation? Initial interpretations of the Webb data suggested that Proxima B's biosphere might employ novel survival strategies. Perhaps life there exists in subsurface colonies shielded from radiation or utilizes reflective pigments that act as natural UV filters. These possibilities pointed toward a new frontier in understanding biology beyond Earth. Equally profound were the philosophical and existential ramifications. For thousands of years, thinkers and scientists have speculated about the possibility of life beyond Earth, often finding themselves limited by a lack of evidence. Now, the data pointed strongly in favor of that possibility. The realization that Earth may not be the only cradle of life prompted a re-evaluation of humanity's place in the cosmos. The idea of isolation of Earth as a solitary, life-barren dot in a vast and empty universe was no longer tenable. This paradigm shift also reverberated through theology and culture. Many belief systems, both ancient and modern, had considered Earth to be a uniquely chosen or special domain of life. The presence of life elsewhere, particularly so close in astronomical terms, demanded a rethinking of these beliefs. Questions about humanity's purpose, morality, and destiny took on new dimensions. Life, it now appeared, was not confined to Earth, but might be woven into the very structure of the universe. The technological implications were just as significant. With evidence of life only for light years away, the urgency to develop advanced space travel technologies became more pressing. Projects like Breakthrough Starshot, once seen as futuristic speculation envisioning tiny probes traveling at 20% the speed of light, gained renewed momentum and investment. A robotic mission to Proxima B shifted from theoretical to inevitable. Development efforts focused on cryogenic shielding, radiation-resistant electronics, and AI-driven autonomous probes surged as the engineering challenge became clearly defined. This discovery also rippled through scientific disciplines. New fields such as xenochemistry, exogeology, and exoclimatology emerged, not based on theoretical models, but grounded in real, observable data from a living alien world. Laboratories around the world began recreating Proxima-like conditions to study extremophile organisms and simulate potential alien biospheres. Meanwhile, the cultural response was immediate and powerful. Art, literature, music, and cinema embraced the Proxima B revelation. Artists visualized alien landscapes and imagined native life forms. Writers crafted stories of first contact, ethical dilemmas, and humanity's expansion into a populated universe. The collective imagination, long fascinated by distant stars, now had a tangible destination to anchor its dreams. Though Proxima B remains physically unreachable for now, it has become a known world through the lens of the James Webb Space Telescope. Its skies may be filled with clouds, its land soaked by rain, and most astonishingly, its atmosphere might be breathing, inhabited by living processes that are not of Earth but no longer mere speculation. Proxima B has become the most scientifically significant planet known beyond our solar system, a second genesis point, proving that the cosmos is capable of producing life more than once. The James Webb Space Telescope, already celebrated as a marvel of engineering and successor to Hubble, had achieved something unprecedented. It had not only observed the early universe or analyzed distant planetary systems, it had reached across the vastness of space and time to uncover signs of life beyond Earth. It didn't just capture images, it uncovered truth, and that truth has irrevocably reshaped science,